Hello everyone, in previous videos, we discussed sections 392.22, A, and B, which cover the sizing of cable trays for both multiconductor and single conductors rated at 2000 volts or less. Since these conductors are typically installed in groups in one cable tray, what are the code rules for applying adjustment factors? Section 392.80, A, covers the ampacity of cables rated 2000 volts or less in cable trays. It provides guidelines for calculating the permissible ampacity of conductors and cables within the tray. This section includes three scenarios. First, multiconductor cables in cable trays. Second, single conductors in cable trays. And third, a combination of both multiconductor and single conductors in cable trays. In the first part of this video, we will concentrate on the ampacity of multiconductor cables in cable trays, specifically under subsection 392.80, A1. Let's get started. Section 392.80, A1, multiconductor cables. The permissible ampacity of multiconductor cables, typically rated 2000 volts or less, installed by the requirements of 392.22, A, shall be as specified in Table 310.16 and Table 310.18, subject to the conditions outlined in 392.80. A1, A, 392.80, A1, B, 392.80, A1, C, and 310.14, A2. Section 392.22, A, addresses the number of multiconductor cables rated at 2000 volts or less that can be installed in cable trays. Since these multiconductors are often placed in close proximity, this section mandates that the ampacity of these conductors must comply with Table 310.16. Table 310.16 provides ampacity ratings for insulated conductors with no more than 3 current-carrying conductors in a raceway, cable, or earth at an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. Conversely, Table 310.18 pertains to the ampacities of insulated conductors with no more than 3 current-carrying conductors in a raceway or cable at an ambient temperature of 40 degrees Celsius, 104 degrees Fahrenheit. This means that if there are more than 3 current-carrying conductors, the multiconductors will be subject to adjustment factors. However, applying these adjustment factors must adhere to the conditions specified in 392.80, A1, A, 392.80, A1, B, 392.80, A1, C, and 310.14, A2. To begin with, let's review the condition in Section 310.14, A2, which pertains to the selection of ampacity. According to this section, when multiple ampacities apply to a given circuit length, the lowest value must be selected. In this example, the multiconductor cables installed in the cable tray are exposed to 2 distinct temperature zones. The electrical room has an ambient temperature of 24 degrees Celsius, while the cables pass through a production area where the temperature reaches 45 degrees Celsius. The cables are 4-aught AWG-XHHW, PVC, 3-core type TC power cables. Based on Table 310.16, the ampacity for these conductors is 230 amperes, but this rating assumes no more than 3 current-carrying conductors in a raceway, cable, or earth at an ambient temperature of 30 degrees Celsius, 86 degrees Fahrenheit. In the electrical room with an ambient temperature of 24 degrees Celsius, the ampacity increases by 1.05%, raising it to 241.05 amperes. However, as the cables pass through the production area at 45 degrees Celsius, the ampacity decreases by 0.71%, reducing it to 163 amperes. Following Section 310.14, A2, the lowest applicable ampacity for the entire circuit length must be used. Therefore, the ampacity of the multiconductor cables is 163 amperes. Subsection 392.80, A1, A, specifies that the adjustment factors described in 310.15, C1, applies solely to multiconductor cables that have more than 3 current-carrying conductors. These adjustment factors are based only on the number of current-carrying conductors within the cable, not the total number of conductors in the cable tray. Consider a 4-wire system for a 3-phase, Y-connected circuit using a 5-core multiconductor cable. In this setup, 3 wires are designated for phases 1, 2, and 3, one wire is for the neutral, and the fifth wire is for equipment grounding. Assume each phase and neutral conductor has an ampacity of 100 amperes. If 5 typical multiconductors are installed in a single cable tray, section 310.15, C1, becomes particularly relevant for multiconductor cables with more than 3 current-carrying conductors. This is important because the heat generated by the current flowing through these conductors increases when they are placed in close proximity to one another. Consequently, the allowable ampacity for each conductor must be reduced, as indicated in Table 310.15, C1. According to Section 392.80, A1, the application of adjustment factors is limited to the number of current-carrying conductors within each cable, not the overall number of conductors in the cable tray. Therefore, even if these multiconductors are grouped with others, the total number of current-carrying conductors does not amount to 20. The adjustment factor is applied individually to each multiconductor. Each multiconductor has 4 current-carrying conductors, resulting in a new ampacity of each conductor calculated as 100 amperes multiplied by 80%, which equals 80 amperes. The reason adjustment factors focus solely on the number of current-carrying conductors within the cable, rather than the total number of conductors in the cable tray. Multiconductors are protected from heat generated by other multiconductors due to their construction, which typically includes insulation and sheathing that provide thermal barriers. This insulation helps to minimize heat transfer between conductors, allowing each cable to dissipate heat more effectively. Subsections 392.80, A1, B. When cable trays are continuously covered for more than 1.8 meters, 6 feet, with solid, unventilated covers, the allowable ampacities for multiconductor cables shall not exceed 95% of the values listed in Table 310.16 and Table 310.18. Going back to the previous example of a 4-wire system for a 3-phase, Y-connected circuit using a 5-core multiconductor cable, each cable has an ampacity of 100 amperes according to the ampacity table. If the cable tray is continuously covered for more than 1.8 meters, 6 feet, with solid, unventilated covers, the allowable ampacity is limited to 95% of that value, which results in a maximum of 95 amperes. Since there are more than 3 current-carrying conductors in each cable, subsection 392.80, A1, must also be applied. Therefore, the final ampacity of the multiconductor cable would be calculated as 95 amperes multiplied by 80%, resulting in a total of 76 amperes. In another scenario, if the cable tray cover is less than 1.8 meters, 6 feet, the ampacity of the multiconductors would remain at 100 amperes. Applying the adjustment from subsection 392.80, A1, would yield a final ampacity of 80 amperes, 100 amperes multiplied by 80%. Subsection 392.80, A1, C. When multiconductor cables are installed in a single layer within uncovered trays, maintaining a spacing of at least 1 cable diameter between each cable, the ampacity must not exceed the allowable ambient temperature corrected ampacities for multiconductor cables containing no more than 3 insulated conductors rated from 0 to 2000 volts in free air, as specified in 310.14, B. For example, consider 3 4/0 AWG cables, specifically XHHW, PVC, 3-core, and Type TC power cables. The nominal diameter of the 4/0 AWG cable is 4.518 inches. According to subsection 392.80, A1, C, these multiconductor cables are installed in a single layer within uncovered trays, ensuring a spacing of at least 1 cable diameter between them. In this scenario, the ampacity can be calculated using the Nair-McGrath method under engineering supervision, as outlined in 310.14, B. In this calculation, the current, I, in amperes is derived from the difference between the conductor temperature, T sub C, and the ambient temperature, T sub A, multiplied by a resistance factor. This calculation includes the resistance of a 305 mm or 1-foot conductor at a given temperature, R sub dC, as well as the effects of skin and proximity resistance, Y sub C, and the effective thermal resistance between the conductor and the surrounding environment, R sub Ca. The formula, created by J. H. Nair and M. H. McGrath, is designed to evaluate the temperature rise due to electrical current flow in conductors. It considers all factors that hinder heat dissipation from a loaded conductor, including the heat-conducting properties of raceway walls and surrounding soil. Further, This analysis is complicated by factors such as airspaces within the wiring, hysteresis losses in magnetic conduits, and skin effects, which can vary based on conductor size. Proper application of the Nair-McGrath formula necessitates a highly experienced electrical engineer who specializes in these calculations, which is why Section 310.14b requires engineering supervision. Furthermore, the informational note of this subsection points to a table in Annex B, Table B2.3, which provides ampacities, for use under engineering supervision, calculated under conditions that effectively mimic a free air environment. In Part 2 of this topic, we will cover Section 392.80a.2, regarding the ampacity of cables rated 2000 volts or less in cable trays, specifically for single conductors. Thank you all for watching.